Okay, so after I stopped recording, I actually went back and did my 2 runs and got a much better reading here on the amounts. Alright, so first of all, let's put down the molarity. Now this was on the label in that container I was using. Now I was supposed to use 0.02 molar, but I only had this higher concentration stuff, which is why the titrations took so little. Alright, but when it was all said and done the second time, excuse me, now this was 10 milliliters, and it was 10.00 because of how that pipette works. So 0.01000, we're actually that good of a number using those volumetric pipettes. But the H2SO4, because I used this higher concentration, this didn't get much above 3 milliliters. So it's going to actually hurt our precision, because that first time I did it where I got it to dropwise, I got 3.25. It was almost perfectly between the 2 hash marks. But this one down here, I mean, this number will be the same. And the molarity of the H2SO4 was the exact same stuff again. But my volume here was 3.40, almost on the nose. So right on the line. So they weren't exactly the same, but that's okay. When we do the math, we'll see that that's going to be fine. All right, so the calculations we're going to do here and down here are the same. So I'm going to write out how I did these calculations here. So to get the moles of H2SO4, a common thing people want to do is get the molecular weight there. We're not going to do that in this case. We have a volume and we have the concentration. We're essentially just going to multiply those. So 0.0325 times the molarity to get the moles. And in this case, we have 0.000 or 1.677. I only have 3 digits. So 1.68 times 10 to the negative 4th. Now because this was a neutralization reaction, our balanced equation showed it was every 1 H2SO4 there would be 1 barium hydroxide neutralized. So these moles are the exact same thing. And then to get our molarity, we're just going to divide that by our volume in liters to get divided by this volume, 0.01. And we get that the molarity is 0.0168. Alright, down below, the only thing that's really going to change is this is going to throw off our amount of moles. We're going to have 0.00340 times 0.0516. And I get 1.75 times 10 to the negative 4th. So this is also 1.75 times 10 to the negative 4th. And this molarity is going to be 0.0175 molar. Now, technically these two are right on the edge, about far apart of where I'd want to do another run. So anything more than that, we probably should have done another run to see which one I was wrong on. And to be quite honest, I'm not really sure which one I messed up on here. We're reasonably close, within 1/10 of a milliliter. What would have drastically helped my results is if I had used the right chemicals. So it's something that I go out of my way to make sure you guys get. If I give you that 0.02, and keep it like it's supposed to be, this is going to be almost double or more than double the amount, and that's really going to help our precision. We just got too little in there, added up a lot of error into this. But average on this, it is just to simply add those two up and divide by 2. So I'll take that and, oh, I didn't actually multiply it, so I didn't actually convert that to my quit. So 0.0175 plus 0.0168 divided by 2. I get an average of 0.0171. I'd be reasonably happy if the error is in that rounding digit anyway. So we're good. Relatively good luck. It should work better when you guys get a chance because I'll be using the right chemicals.